Good afternoon, grade 12 learners. Welcome to our today's lesson in physical sciences. The lesson that is given to you today is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center, and it is live broadcast by Pagama Research and Development. My name is Tandiwe Uwane. I will be taking you through physical sciences on the chemistry lesson. Our today's lesson is going to focus on the acids and bases. I think by now we have looked at different reactions. We started by looking at the rates that affects the reactions. We went further to look at the chemical equilibrium. So today we are going to look at the new concept, which is acids and bases. I know that acids and bases are not new or new topic to you. You did acids and bases in your previous grades. So today we are going to look at the acids and bases according to two principles. So as we are going to look at this topic, we will always refer to the two principles that we are going to talk about, because as we are going to define them, or we are going to look at the properties of acids and bases, we will definitely concentrate on the two principles that we are going to discuss today. Now, let's start with our lesson. What are the objectives of today's lesson? These objectives, they are taken directly from the exam guideline, and you must make sure that you make your exam guideline handy so that always when we have a lesson, you always refer to it to know what is it that is expected of you by the end of each lesson. So according to the objective of this lesson, we are going to distinguish between strong acids and bases, weak acids and bases. We are also going to look at concentrated acids and bases and diluted acids and bases. We look at the acids and bases according to Arrhenius and Lowry-Bronsted theories or principles. These are the theories that I said we will look at the properties of acids and bases according to the two theories, which is Arrhenius and Lowry-Bronsted theories. We are also going to we are going to write down the reactions equations of aqueous solution of acids and bases, identify acid-base conjugate pairs for a given compound, and we are also going to look at the neutralization reactions of common acids and bases, and we are going to determine the approximate pH of a salt in hydrolysis, and we are also going to calculate pH. So these are the objectives of today's lesson. We will make sure that by the end of the lesson, all the outline objectives are being covered. Now let's look at the pre-knowledge of what you know about acids and bases. We are going to just look at the properties of acids and bases that you know, because these acids and bases are used in our daily lives. You see them almost every day in your life. So how are the acids and bases in our daily life? The acids are having sour taste. So you can think about the lemon juice, you can think about the vinegar, you can immediately think about, oh, it means because of the sour taste, they can be classified as acids. We have sour taste, and then acids, they also produces hydrogen ions. This is a chemical property of acids and bases. This is something that you cannot see through your naked eyes or you cannot taste, but it's something that occurs chemically. So acids can produce what? Hydrogen ions. And then they can also conduct electricity, and they can neutralize a base. So it means that if you want to neutralize a base, the best compound that you can use is an acid, because one of the property of acids is that they can neutralize a base. Then let's look at the bases. Bases, most of the bases have bitter taste. I think the simple example of a base that I can give to you right now is a soap, like a powder soap or a bath soap. As you can see them, they are slippery, they are having a bitter taste. They are good examples of bases. However, I cannot encourage you to test acids and bases using your mouth, but these are some of the tastes that you can accidentally feel about acids and bases, because as you know that you are going to deal with laboratory acids and laboratory bases, you are not advised to use your mouth or to use your skin to test whether it's an acid or it's a base. What else about the bases? They produce hydroxide ions. It's not hydrogen ions, but it's hydroxide ions. So bases produces hydroxide ions, and they also conduct electricity like the acids, and then the bases, they will neutralize acids. So we can see that now acids can neutralize bases and bases can neutralize acids. It means acid-base reaction, we can refer to it as a neutralization reaction, because when an acid reacts with a base, they neutralize each other, because they can react very well to each other and they can also neutralize each other. So these are a few properties of acids and bases that I want us to start with, so that we have a pre-knowledge of what we are going to talk about this afternoon. Now, let's look at the two principles that I said they are going to govern our acids and bases, as we're going to start with their properties and their chemical properties. We are going to firstly look at the acids definition according to Arena's principle. What does Arena's principle say are acid? According to Arena's, acids are substances that can produce hydrogen ions. I think we have seen from the properties that we just discussed that the other property of acids is that they can produce hydrogen ions. So according to Arena's, Arena says acids can produce hydrogen ions in a solution. And then if you have a hydrochloric acid, which is one of the examples of the acid, because we are still going to look at the examples of acids. If you have hydrochloric acid will ionize to hydrogen ion and chloride ion. So you can see by ionizing to hydrogen ion, you can see that now hydrochloric acid is producing hydrogen ion. And this is according to Arena's principle. It is very important to know what does each principle say about acids and bases. So we are starting with Arena's principle, and Arena's principle says acids are substances that can produce hydrogen ions in a solution. And this is an example on how an acid can ionize to form those hydrogen ions. And then this hydrogen ion, if this hydrochloric acid is reacting with water, this hydrogen ion can easily combine with water, because it can quickly combine with water and form hydronium ion. So it is not a mistake when you say acid produces hydronium ion in water, or acid produces hydrogen ion. Hydronium ions will be produced when water is involved, but in normal situations where there's no water, what we are going to see is hydrogen ions. So according to Arena's principle, acids are substances that can produce hydrogen ions in a solution. Then we are going to look at the definition of bases according to Arena's principle. What are bases according to Arena's principle? Bases are substances that produces hydroxide ions, and the definition of hydroxide, the formula of hydroxide ions is OH minus in a solution. So as the acid, it produces hydrogen ions in a solution, the base will then produce hydroxide ion in a solution. So these are definitions of acids and bases according to Arena's principle. And it is very important that you know that as these acids and bases are going to produce those hydrogen and hydroxide ions, what is going to happen to those hydrogen and hydroxide ions? Now, this is an example of a base, which is sodium hydroxide, whereby it dissociates in water into its ion, and it forms a sodium ion and a hydroxide ion. So you can see from the two examples that I've given of a base, whereby also ammonia as a base reacts with water to give you ammonium ion and hydroxide ion. So whether that acid is having the OH or the base is having the OH or not, definitely the hydroxide ions will be formed. And that will be betterly explained by the next principle that we are going to talk about. So what I want to now to recap is that acid and bases, they can be defined according to Arena's principle. What does Arena's principle says in terms of the acids? Arena's principle says acids are substances that can produce hydrogen ions in a solution, and bases are substances that can produce hydroxide ions in a solution. Let's look at the next principle, which is Lorentz-Bronsted principle. According to Lorentz-Bronsted principle, acids are substances that can donate hydrogen ions. I think we have seen that according to Arena said acids can produce hydrogen ions. So those hydrogen ions that an acid can produce, it can also be able to donate it. So an acid is a substance that can produce hydrogen, that can donate hydrogen ion. Or we can easily say acid is a proton donor. What do we mean by a proton in this regard? Remember, as we have a hydrogen ion, what is an atomic structure of an hydrogen ion? We know that hydrogen atom the atomic structure of hydrogen atom, as it is having a nucleus, it will have one proton and one electron. Therefore, if this one electron is being shared, it means what will be left is only a proton in a hydrogen. Therefore, it will form an H plus, showing that there is only a proton that is left as the electron is being shared by another with another compound or another atom. Therefore, that is why it is referred to as a proton. This proton, it simply means hydrogen ion. So they are referring to it as a proton because it's the only thing that is left in that ion after that electron inside that structure has been shared with another atom. So we refer to a proton as hydrogen ion. So our proton in this regard is our hydrogen ion. Don't confuse yourself by saying now our protons now are being donated, whereas we told you that the things that can be shared and that can be transferred are electrons. But what we know is that protons inside the nucleus are the ones that will be kept. So inside the reaction whereby a hydrogen is reacting with another atom, that electron will be taken away, and whatever that will be left is the proton. So that is why we refer a hydrogen ion as a proton. So in simple ways, we can say, according to Laurie Bronsted, an acid is a proton donor. An acid is a proton donor, or an acid is a substance that donate a hydrogen ion. And then according to Laurie Bronsted, a base is a proton acceptor. I think we know by now that ions cannot be lost and they cannot be created, but they can be transferred. So what is happening is that immediately when an acid donates that hydrogen ion, where will that hydrogen ion go? That hydrogen ion will be accepted by the base. So that is why we say an acid is a proton donor, whereas a base is a proton acceptor. This is according to Laurie Bronsted principle. So you must not mix the two principles. You must know who said what. You must know what was said by Arenas in terms of acids and bases. And you must also know what was said by Laurie Bronsted in terms of acids and bases. So the examiner can just ask and say, define an acid according to Laurie Bronsted. So you know that according to Laurie Bronsted said acids are proton donor. Or they can say, define a base according to Arenas. According to Arenas says bases are substances that can produce hydroxide ions. It is very important to know the difference between the two theories. However, they are not different because whatever that was produced during the Arenas principle under the acids is the one that will be donated by that acid, and it is also what will be accepted by the base. Now let's look at the example whereby we look at the acid and the base reaction in terms of Laurie Bronsted principle. When hydrochloric acid react with ammonia, hydrochloric acid is an acid, ammonia is a base. So what will happen is that hydrochloric acid, as it is having a hydrogen ion, it will donate the hydrogen ion to the ammonia. And what will happen? Ammonia will accept that hydrogen ion. So it means now this hydrochloric acid, as it is an acid, is a proton donor. And this ammonia, because it's our base in this reaction, it is our proton acceptor. And immediately when the acid, hydrochloric acid, loses a proton, it becomes Cl minus because an H plus was removed from it. And this minus shows that a hydrogen was removed from this structure. So for it to become minus, it shows that there was something that was supposed to be added for this compound to be neutral. So it is no longer a neutral compound, or it is no longer a neutral substance because something was removed and it formed an ion. So that is why we said it ionized. And then immediately when you can see on the ammonia side, ammonia, after accepting the proton or the hydrogen ion from an acid, it becomes an ammonium ion. Ammonium ion. So ammonium ion also by the plus, it means something was added to it. It was NH3, now it is NH4 plus. These plus and minus are very important because they are showing that they are now in a form of a charge, or they are now in a form of ions. So you need to always indicate them. This side, they are both neutral compounds. However, when they go to the other side, this one becomes Cl minus to show that hydrogen ion was removed from it, and this one becomes NH4 plus to show that we have added a hydrogen ion in ammonia. So these are two principles. So the acids and the bases that we are going to talk about for the entire lesson, they must behave like this. I am not saying all acids behave like this. I am saying only the ones that we are going to talk about in this lesson, they must be able to produce hydrogen ions, and they must also be able to donate those hydrogen ions. The bases must be able to donate, to accept hydrogen ions. They must also be able to produce hydroxide ions. So you must make sure that always when you look at the acids and the bases that we are going to deal with, it means now you cannot have an acid according to our two principles without a hydrogen. So the hydrogen will be your starting point of every acid that we are going to talk about for this lesson. If you don't have an acid, you cannot qualify. If you don't have hydrogen ion, you cannot qualify to be an acid according to the two principles that we talked about, because you cannot give what you don't have. If you are saying it's an acid but it doesn't have a hydrogen ion, it means it will not obey the Arrhenius and the Lorentz principle. We know that there are those acids that don't have hydrogen ions, but they are not the ones that we are going to discuss in our topic for today. The acids that we are going to discuss are the ones that are having hydrogens, so that they can produce those hydrogens and they can also donate those hydrogen ions, and then they can be accepted by the base. So the bases that we are going to talk about, they are bases that can be able to accept the hydrogen ions, and they are the bases that can also do what? The bases that can also produce hydroxide ions. Now, these are the definitions that I was talking about. Acids, according to Lori Bronsted, proton donor, basis, proton acceptor. Now we go to another concept. We can further classify acids as strong acids and strong acids and weak acids. Now, the first thing that you need to know the definition of what do we mean by strong acids. A strong acid, according to the definition, is an acid that can ionize completely. I have made the ionize completely to be in red, so that you can see that is the most important concept that you must remember. Acids which are strong, which are classified as strong acids, they ionize this completely. And then they can ionize completely in water to form a high concentration of hydronium ions. So we know that when is the hydronium ion forming? Is that when the hydrogen ion combined with water, it will form hydronium ion. So these strong acids, they ionize this completely. That is very important. So if I can classify an acid as a strong acid, what do I say to you? I'm already telling you that acid, you are expecting it to ionize completely. And what are the examples of strong acids? These are the examples of strong acids according to our exam guideline. Our exam guideline gave us hydrochloric acid or hydrogen chloride acid, sulfuric acid, and nitric acid. These three acids are classified as strong acids according to our exam guideline. However, there is another way of you being able to identify whether an acid is a strong acid or a weak acid. We're going to use what we call an equilibrium constant of acids and the equilibrium constant of bases. So the equilibrium constant of an acid or of a base will tell you when an acid is a strong acid or when an acid is a weak acid. If an equilibrium, a Ka value, is greater than 1, it indicates that it's a strong acid. And if an equilibrium constant is of a base is greater than 1, it shows that it's a strong base. So what is important that the examiner sometimes can give you a Ka value. That Ka value will tell you whether the acid is strong or weak. So you just look at the number of the Ka value. If it is greater than 1, it is indicating that the acid is a strong acid. And what do you mean by strong acid? It ionizes completely in water to form a high concentration of hydrogen ion or hydronium ions. So the word ionizes completely, I want you to make sure that you master it, because it's what explain or classify a strong acid. So as you look at our strong acid, you can see that this one, hydrochloric acid, is having 1 hydrogen, sulfuric acid is having 2 hydrogens, nitric acid is having 1. So we can further classify this strong acid as either about the number of atoms or the number of hydrogens that they can donate, or the number of protons that they can donate. I always say you cannot give what you don't have. So immediately when you look at hydrochloric acid, it's having 1 hydrogen. So for it being having 1 hydrogen, it means it can be able to donate only 1 hydrogen. So for that capability of it being able to donate only one hydrogen ion, it is known as monoprotic acid. So what is a monoprotic acid? A monoprotic acid is an acid that can donate one proton, or that can donate one hydrogen ion. So we refer to it as a mono for one, protic for the proton. So monoprotic is an example of an acid that can donate one proton. And then we have sulfuric acid. If you look at the sulfuric acid molecular formula, you can see that it is having two hydrogens. So for it to have two hydrogens, it means it can have also that capability to donate two protons or two hydrogen ions. So we refer to it as a diprotic acid. So what are diprotic acids? Diprotic acids are acids that can donate two protons. You don't say more than one. You know exactly, you know the number exactly how much. So you just say two. If it is one, is one. If it is two, is two. And because it's a diprotic acid, it means now it will normally ionize in two steps. This one, monoprotic, they always ionize in one step. But diprotic acid, as the number of protons increases, that acid is having a capability of ionizing even more than once, because it can give and also give for the second time. So that is why we're saying monoprotic acid ionizes once, whereas diprotic acid ionizes twice. We do have the triprotic acids and the tetraprotic acid, but they are not covered according to our exam guideline. We will only look at the monoprotic acids and the diprotic acids. Then we are going to look at the last one, which is nitric acid. As you can also see, nitric acid is having one hydrogen, so it also qualified to be a monoprotic acid. So those are the concepts that you need to understand as we are starting this topic, and those are the definitions also that you need to understand as we are starting this topic, so that when they are saying an acid is ionizing in two steps, you know why it is ionizing in two steps, because you know why that acid can provide or can donate more than more than one proton. It can donate two or three protons. So that is why it can donate, it can ionize in different steps. So monoprotic ionizes once, whereas diprotic ionizes in two steps. Now, if you look at nitric acid, you can see that as nitric acid ionizes, it forms a hydrogen ion and a nitrate ion. So this is an example of a strong acid ionizing completely. And the ions that are going to form on the side of the product, you will see that they will form a very small ions, nitrate ion and hydrogen ion, showing that it has ionized completely. So as it ionizes completely, what does it mean? It means now the concentration of nitric acid will be the same as the concentration of the ions that it produces. So if you know the concentration of nitric acid as a strong acid, you already know the concentration of hydrogen ion and nitrate ions, because as it ionizes completely, it will make sure that also the ions, because it is partially ionizing 100%. So you can know that the ions that are going to form, they will never change the concentration of that acid, because that acid is referred as a strong acid and it ionizes completely. So if this is 0.1 mole per deciliter cube as the concentration, we also know that this one is also going to be 0.1 mole per decimeter cube concentration, because this acid ionizes completely. So the information of an acid ionizing completely, it will give some information about the concentration of the ions that are going to be formed. It will also tell you the size of the ions that are going to be formed in terms of the amount after separating to, or after ionizing to its ions. Then weak acids are those acids that ionizes incompletely. So they are the opposite of strong acids. They ionizes incompletely. And they are showing also, they are doing what? They are forming also low concentration of hydronium ion in a solution. So weak acid examples are ethanoic acid, which is one of the example of carboxylic acid. And also the oxalic acid is also another example of carboxylic acid. So these carboxylic acids, as you can see them, they are weak acids. And as they are weak acids, they are forming weak acids because when they ionize, they will ionize incompletely. Like when you look at ethanoic acid ionizing to the hydrogen ion and ethanoate ion. So you can see the amount of the ethanoate ion that is still left for this compound to still ionize further. So that is why we are saying this ionizes incompletely. You can also use the word partially or incompletely, but because we said the other one ionizes completely, the other one will ionize incompletely in water. Now, these two are the examples of oxalic acid, the examples of weak acid, which is oxalic acid and ethanoic acid. What are we saying? We are saying an acid which is a weak acid ionizes incompletely, whereas strong acid ionizes completely. Those are the two things that you need to make sure that you understand about this. And also the examples that I've already provided. You must see that when I say ethanoic acid or CH3COOH, you must immediately identify that acid as a weak acid. And the reason is because it ionizes incompletely. Okay? Now we look at the strong bases. What is a strong base? A strong base is a base that can dissociate. You see now the language is changing. Why are bases dissociating? By ionizing, I mean they form ions. They form ions when they are in a solution. But dissociation, it means they separate into their ions. So dissociation is not the formation of ions, but is the separation into its ions. When you look at sodium hydroxide, it will form sodium ion and hydroxide ion. The sodium ion and the hydroxide ion is not that because it was ionization. No, it was just a dissociation. It's just like sugar. When you pour sugar inside water, what sugar will do, it will just dissociate. So it's exactly the way the bases are acting. They dissociate. However, the acids do not dissociate, but they ionize. So ionize is forming ions, dissociate is separating to its ions. So it will be further explained as we are going to look at other examples, but just know that strong bases dissociate completely. And we said strong acids ionizes completely. So you need to know the difference. You need not to use this word interchanging because they don't mean one and the same thing. Ionize means they form ions in a solution. Dissociate means they separate into their ions during the. So when you look at strong bases, you can see that we have sodium hydroxide, we have potassium hydroxide, we have lithium hydroxide. All those are examples of strong bases. My wonderful learners, it is very important to know these examples because as you are provided with that acid or that base, you must immediately be able to classify it as strong or weak, especially those that are provided on your exam guideline. And then those that are not provided to you on the exam guideline, normally the examiner will give you a clue to say it's a strong acid or a weak acid, or they can also give you the Ka value or the Kb value as I explained on our previous slide. So it is very important that you can see that this is a strong acid. And if immediately when you know that it's a strong acid, you know that it ionizes completely. Immediately when you see that it's a strong base, you know that it dissociates completely. And these are examples of strong bases. Then when you look at the weak bases, these are the examples of these weak bases. Ammonia, the carbonates, the metal carbonates are also weak bases. And then the ammonia, the sodium carbonate, the calcium carbonate, they are all examples of weak bases. And they are also provided to you on your exam guideline. So you can also study them and know them and classify them as weak bases. What do we mean by weak bases? Weak bases dissociate incompletely. However, sometimes weak bases, you will see on your exam guideline, they can also ionize. Weak bases, unlike the strong bases, they can sometimes form ions. But for us not to be confused, let's just say strong acids and weak acids, they ionize, and then weak bases and strong bases, they dissociate, so that we don't get confused with two ways. We make bases to dissociate, we make acids to ionize, so that we don't make mistakes in terms of the definition. So weak bases, they ionize, they dissociate incompletely, and they will also form a low concentration of hydroxide ion. Remember, the strong bases form the high concentration of hydroxide ions, whereas the weak bases form the low concentration of hydroxide ions. So you can see here ammonia as it is reacting with water. What is going to happen? Ammonia will form ammonium, and when you look at ammonia and ammonium, they almost look the same, to show that there was an incomplete dissociation. So they will form ammonium ion and hydroxide ion. So this is an example that shows that weak bases dissociate incompletely in water, and it will also form what? A low concentration of hydroxide ions. So already we know the definition of strong acids and the examples of strong acids, the definition of weak acids and the examples of weak acids, strong bases and the definition and the examples, and then weak bases, the definition and the examples. This is very important. This is our starting point, because whenever we'll be doing all the reactions, we will be always working with these kind of compounds. So you need to be able to identify them and know the definition and classify them. Now, what do we mean by concentration? I think in my previous lesson, I explained what is concentration, and I also showed you how do we calculate concentration. I always say concentration is equals to the number of moles over the volume of a solute. Therefore, these acids and bases, they can also sometimes react with water. However, it will always depend on the amount of water that is reacting with that acid, whether it's more of water or less of water. Now, if there is less water, obviously what is going to happen? It means if there's less water, there will be more concentration. That thing will be concentrated. So it means the value of C will be high. But if there's more water, the value of C will be low. So what do we mean by the value of concentration being high or being low? When the value of concentration is high, we are saying that acid or that base is concentrated. There's a difference between strong and concentrated. Concentrated means there is more of an acid, what is it? More of an acid or base than the number of the amount of water that is present. Meaning that sometimes there's no water at all. If you are saying a base or an acid is concentrated, there is no water, or sometimes there's little of water present. However, when we say an acid or base is diluted, there is more water in that acid or base. So when an acid is concentrated, it can be concentrated still being weak, or it can be concentrated but strong acid. By being strong or by being weak is not because of its concentration. What makes them to be strong or weak is the way they ionize or the way they dissociate. So if we have maybe a ethanoic acid, we know that it is falling under the examples of weak acids. Ethanoic acid can sometimes be diluted, or it can sometimes be concentrated. When it is concentrated, it doesn't mean now that it becoming stronger. No, it just means there is little or no water in that ethanoic acid. So always when you talk about being concentrated or diluted, you refer to it in the proportion of water that acid or that base have as compared to water. So concentrated, diluted must not be confused with weak and strong, because we know that concentrated means little water than an acid or base. Diluted means more water than an acid or base. And we know that if we look at the concentration, if I have 1 mole per decimeter cube of an acid, and I have 0.1 mole per decimeter cube of an acid, I will already know that 1 mole is concentrated than 0.1. So 0.1 is diluted as compared to 1 mole. The number will always tell you whether that acid is diluted or concentrated. And always, most of the time when we start with the whole numbers and we don't start with 0, which are decimals, you will see that not any decimal, but 0, something, you will see that that acid or that base is already diluted, because it shows the proportionality to say there is more water than that acid, or there is no more water than the base. But if it is concentrated, you will see that there will be a whole number before you start with another number to show that that acid is concentrated. So concentrated, diluted, it is with relative to water in that acid and base. Strong and weak is about the ionization and the dissociation. So it must be very clear to you to say same strong acid can be diluted. Same weak acid can also be concentrated, vice versa with the bases. Strongness and weakness has nothing to do with being concentrated or diluted. Now, we have seen that acids and bases can react with each other. And according to Laurie Bronsted, as the acids were reacting with bases, acids were donating protons and bases were accepting those protons. So immediately when an acid donates a proton, that acidity or that state of being an acid, the acid will lose it. Meaning that as an acid will lose a proton, will now become a base. And after a base accepting that proton on the side of the product, it will become an acid. Let's look at this reaction of hydrochloric acid and water. In this regard, we know that water cannot be classified as an acid and it can also not be classified as a base. But what happens when an acid reacts with water? When an acid reacts with water, it will make water to act as a base. Why is acid making water to act as a base? Because this hydrochloric acid, as one of the example of a strong acid, will donate a proton to water and water will accept that proton. So as it is donating a proton, you can see that it will now change and become a chloride ion. So it is no longer an acid because it doesn't have a hydrogen. It has lost the status of having an acidity. So it becomes a base now. So when you look at this hydrochloric acid and this base, you can see that there's something that is common about them. They both have Cl, but this one is having a hydrogen, whereas this one doesn't have. So this can be classified as acid-base conjugate pairs. What does the word conjugate mean? The word conjugate means formed from. So this acid, it's forming this base. So this base is formed from this acid. So that is why we classify to them as the conjugate. So this base is the conjugate of this acid because this base was formed from this acid. Then, sorry about that. When you look at water, you can see now that water will accept the proton from the acid and form a hydronium ion. So in this case, water acted as a base. And after acting as a base, it will accept that proton and it will become an acid. So this H2O plus is the conjugate acid of this base. So you need to be able to identify the acid-base conjugate pairs. What will assist you? You just look at what is similar about the acid on the right-hand side and the base on the left-hand side. Immediately when there is one hydrogen missing on the base, that base is the conjugate base of the acid that we started with because it shows that that acid has donated a proton for that base to be formed. So that is why we say they are conjugate. So we can identify them as, if this is our acid one, our first acid on the reaction, this one is going to be our base one because it's the first base that is coming from this acid on our reaction. And then if this, we are classifying them as a base 2, it means this is going to be our acid 2. So the relationship between acid 1 and base 1 is 1 hydrogen. The relationship between base 2 and acid 1 is also 1 hydrogen. This base is having 2 hydrogens, this acid is having. So an acid will always have more hydrogens as compared to the base. And you can even identify it without even thinking too much because you will just say, what is the relationship? Are they almost similar? What makes them to be different? If it's only 1 hydrogen that makes them to be different in terms of the product and the reactants, then you'll know that they are acid-base conjugate pairs. So we know that this is an acid, hydrochloric acid. Its conjugate base is going to be Cl minus. If water is a base, its conjugate acid will be H3O plus. So that is the relationship. If you look at the number of hydrogen this side and this side, you can see that an acid will have what? More hydrogen as compared to its conjugate base. And a base will have less hydrogen as compared to its conjugate acid. So it's not a difficult concept. It's just that the word conjugate maybe might be coming for the first time in your concept, in your vocabulary. However, conjugate means formed from. So this acid formed this base. So this base is formed from this acid. That's why we are saying this base is a conjugate of this acid and this acid is a conjugate of this base. As we continue with acid-base conjugate pairs, now what I want us to do, I want us to look at this little activity whereby we are going now to identify acid-base conjugate pairs. When you look at this reaction, you can see that we have now ammonia and water reacting. The first thing that you need to identify is that ammonia is a base or an acid. So immediately when you say ammonia is one of the example of a base, and we know that it's a weak base, therefore you will do what? You will know that ammonia is the base and it's a weak base because it dissociates incompletely. So therefore, if ammonia is the base here, water here will act as an acid. I think we have seen that in our previous slide, this one, we have seen that here water was acting as a base because it was with an acid. Where water is with the base, water will now act as an acid. So what do we mean by the conjugate base? Now, when you look at this base, you are now expecting this acid to donate a proton to a base and the base to accept. So water will donate a proton to ammonia and ammonia will become ammonium ion. And then as water loses a proton, the water will become OH minus, which is a hydroxide ion. So in terms of conjugate acid base pairs, let's look at the first. The first base was water here. We're having our base as was ammonia. Because this there, our ammonia was our base. And what is our acid? Our acid was water. Then let's look at the conjugate side. This ammonia accepted a proton from water and our conjugate acid became NH4 plus. So NH4 plus is our conjugate acid. It was formed after ammonia as a base accepted a proton from water, because ammonia, according to Laurie Bronsted, because it's a base, it must accept a proton from an acid. So as water will donate a proton to ammonia, ammonia will gain that proton and become ammonium ion. Then water here was our acid. It acted as our acid. So it will lose a proton, and after losing a proton, it formed what we called OH minus, which is our hydroxide ion. So our hydroxide ions is gonna be our conjugate base. So sometimes an examiner can say, give the pair of conjugate acid or conjugate the pair of conjugate acid base pairs in this reaction. You know that ammonia will be conjugate base pairs with what? Ammonium. And then water will form a conjugate acid base pair with hydroxide ion. So already you know the pairs. That's how they relate. And what is important is that ammonia is having 3 hydrogens, ammonium is having 4. So the one with more hydrogens will be an acid and the one with less hydrogen will be a base. Even here, water will be an acid because of more hydrogen, and hydroxide ion will be a base because of less hydrogen. So it is very important that you know the difference between acid base pairs and you can identify them. Breaking down and dissociating Milenas is almost one and the same time. It breaks to its ion, break down to its ion, or it separates to its ion. It's not a problem if you say it breaks down or it dissociates or it separates to its ions. That is the question that was asked. So also here, I'm still continuing with acid-base conjugate pairs concept. As you can see, we have a reaction, the first reaction, this one. And you can see here that even though they didn't tell you which one is an acid or which one is a base, but you can see that here, what happened, this hydrogen nitride, after reacting, it becomes a nitride ion. So already you can see that as a nitride ion, it has lost 1 proton. So it means this one is going to be our acid and this one is going to be our base. That is the first thing. Immediately when you identify one as an acid, the other one will immediately be your base. So what is going to happen is that this one acid going to donate a proton here. It's going to donate a proton to this water. This one is H3 plus. Then it's going to donate a proton, and then we have NO2 minus, and then here we're going to have H2O plus. So the pairs are HNO2. It goes with what? With NO2 minus, and then H2O will go with what? With H3O plus. That's how the pairs go. They are conjugate acid base pairs. And then when you look at this one, this reaction, you can see now that we have this phosphorus ion, whereby now we are having hypochlorous ion, hypophosphate ion. Therefore, this one this side, and this one this side. Let's check. If you look at the number of hydrogen this side and this one is having less as compared to this one. So it means this one is going to be our base, and then this one is going to be our acid. NH4 plus, and this one is having more of the hydrogen, so it's going to be our acid, and this one is going to be our base. So the conjugate acid base pairs, you can see that now this ion here has lost a proton and gave it to ammonia, and ammonia became ammonium, or ammonium lost a proton to this one and gave this one a proton and become H2PO4 minus. So I want you to check something. We have HPO4 2 minus, we have H2PO4 minus. Immediately when this ammonium ion donated a proton to this HPO4 ion, what happened is that there were 2 minus, and now it becoming minus because they are now 2. So it means if we can get something that can also donate a proton, it means it's going to be H3PO4, and then we're going to remove this. So it means this is the original compound, and then after losing one proton it became this, and then after losing another proton it becomes this. So you must know that a minus, if it is 2 minus, it means 2 protons are already being removed. If it is 1 minus, it means 1 proton is removed. It is very important to know that, so that you don't forget to say a proton is donated here. So the minus is no longer 2 minus, but it is 1 minus, because these 2, instead of 1 here, there will be 2 here, because the other proton has come into this structure or this compound, and minus here. If the third one comes, there will be 3 here, and there won't be any charge here, to show that now it becomes, as more as the negative ion is accepting the protons, it is moving towards being neutral or being positive. So it is very important to know what is the difference between PO4 2 minus and H2PO4 minus, because that shows that immediately when you add a proton, the negative, you lose the negative sign, because the negative sign says something was removed. So when you bring it back, the negative sign is gonna also reverse. So these are, this one and this one are acid base pairs. This one and this one, they are also acid base pairs. So it is very important to understand what do you mean by acid base conjugate pair. But you just look at the number of hydrogen that are missing in terms of an acid and a hydrogen. Now I think we have seen that when I was doing the reactions in my previous examples, when I was using water, there was a place, there was an instant where water acted as an acid. And when I changed and made water to act with a base, water acted as an acid. When I made it to react with an acid, it became a base. So you can see that water now, it is having a dual purpose. It can react, it can act sometimes as an acid, it can act sometimes as a base. So immediately when a substance can act as both an acid and a base, or can act as an acid and a base, we have a term that we provide to that substance, and we refer to that substance as an ampholyte. So what is an ampholyte? An ampholyte is the substance that can act as both an acid and a base, or is the substance that can act as an acid and a base. I'm saying act like. It is not an acid, but it acts like an acid. It is not a base, but it acts like a base. So it's an ampholyte. Like when you look at the first example that we had water. There was a time where water gained protons, and when water was gaining proton, it was a base, and it became H3O plus. There was a time where water acted like an acid, and when it acted like an acid, it donated a proton and became OH minus. So we know that when OH minus is forming from water, we already know that here it means water was acting as an acid. But when H2O plus is forming, when we are reacting with water, it means here water was acting as a base, because from here to here, it means it has accepted a proton and became H3O plus. But from here to this one, or hydroxide ion, it means it has lost a proton. Then it means it has donated a proton. Then it becomes OH minus. Then we also have sulfuric acid. Remember, I also told you that sulfuric acid can ionize into 2 steps. So it means, as sulfuric acid, we know, is a type of a strong acid. It's classified as a strong acid because sulfuric acid can ionize completely. So it means if sulfuric acid ionizes, it can ionize firstly, first ionization, it can be, let's make it to react with water. It can be H2SO4 plus H2O. What is going to happen? This sulfuric acid will donate a proton to water, and water become H3O plus, because I have removed a proton already in sulfuric acid, it become HSO4 minus. What does minus mean? This minus indicates that this acid has already lost the proton and it becomes a base. So sulfuric acid is having a sulfate ion as its conjugate base. Then if you can look at this structure, this one, you can also see that it can furtherly give away protons because it is still having hydrogens. So it means it can furtherly say HSO4 minus if it can make to be reacting with water. What is going to happen is that now, remember, we're having a minus, we're going to have SO4 2 minus. These 2 minus already show that we have lost 2 protons plus H3O plus. So this HSO4 minus, not actually sulfuric acid, HSO4 minus is our ampholyte, because here it was our base because it was formed from sulfuric acid, but here is our acid because it is donating a proton. So it's not sulfuric acid exactly, but it's a sulfate ion. It's a hydrogen sulfate ion. Hydrogen H SO4 minus hydrogen sulfate ion is our ampholyte because it can act as an acid here and it can act as a base here. So that is why we are referring to it as an ampholyte, because it is having an amphoprotic or amphiprotic purpose. It can work as an acid, it can also work as a base. As long as you have a hydrogen, you can be able to donate that hydrogen. And if you are able to donate that hydrogen, it means now you will act as an acid. And this also can accept a hydrogen from water. If it accepts the hydrogen from water, it will go back and form sulfuric acid. So it can act in both ways. It can be sometimes an acid, it can be sometimes a base. So you need to check whether in that specific reaction it has acted as an acid or it has acted as a base. Just like water. It's not that always when you see water you think it's an ampholyte or it's an acid or it's a base. You need to check whether in that specific reaction, and they normally give 2 reactions whereby they say which one is an ampholyte between these 2 reactions. Not always when you see water you think it's an ampholyte. Sometimes water might not be your ampholyte at that point in time. So you just need to know how to use your acid conjugate base pairs information to check whether water or that a substance is an ampholyte in that reaction. And then also here, from this one, we can get what is it? HCO3 minus. So HCO3 minus, it can also be our example of an ampholyte because as it is going to be H2CO3, as it reacts with water or ammonia, what is going to happen? This one will donate a proton to ammonia and it will become HCO3 minus plus ammonium NH4 plus ion. And then this ammonium ion, as it is formed with this HCO3 minus can react also maybe with water. And what is going to form? This one will give a proton here, and then we have H3O plus CO3 2 minus. Remember, the 2 minus show that now it was at the beginning, it was 2 hydrogens, and now all of them are. So H3O, hydrogen carbonate ion, can also act as our ampholyte. So the example of the ampholyte that we have already discussed, water as one of our ampholyte, hydrogen sulfate ion as our ampholyte, and hydrogen carbonate ion as our ampholyte. So these can be examples. So they have, you know why they are these, especially these 2, why they are good examples of ampholyte is because they have a hydrogen that they can donate, and they have a minus that can show that they can also accept a hydrogen. So they have hydrogen and minus showing that they can donate hydrogen further, or they can accept hydrogen and go back to the neutral state. So these are examples of the ampholyte. Now let's look at this activity. The first thing says indicate acid, indicate the conjugate acid base pairs in the following equations. I will just give you 3 minutes to do A and B by identifying or by indicating acid-base conjugate pairs in these two reactions, and then after that we'll continue with the next concept. So I just want you to do this activity for 3 minutes. So our 3 minutes will start now, whereby you will do number one, which is A and B. You identify acid-base conjugate pair in reaction 1. You also identify acid-base pair conjugate pairs in reaction number 2. So our 3 minutes will start now. The hydrolysis. So definitely I will answer that question when we are doing hydrolysis, but just know that when you refer to the lime water, you are just referring to calcium hydroxide. So it must not be something that is a big word for you. You just know that if you are saying lime water, what exactly are you referring to, and which molecular formula are you referring to? So you are going to be answered in terms of how can you undergo hydrolysis of calcium a hydroxide. But now let's focus on the activity that we just done. Now, when you look at reaction 1, I hope you can see that hydrochloric acid reacts with ammonia. And what comes into your mind, you know that we have already classified hydrochloric acid as an acid, which is a strong acid, ammonia as a base, which is a weak base. Therefore, if a weak acid reacts with a weak base, obviously what we are expecting hydrochloric acid to donate a proton towards ammonia, and ammonia accept that proton. So immediately when hydrochloric acid donates a proton, the first pair that you are going to have which is the acid-base pair, it means this one will be formed from this acid. So it's going to be HCl and what? And Cl minus. That is the first pair that you're going to get in reaction 1. And then we are also going to get what? NH3 and NH4 plus, which is your second pair. So HCl forms Cl minus, NH3 forms NH4 plus. So these two are the conjugate acid base. But these two, as I identify them, they are acid base conjugate pairs. Even these two, they are acid base conjugate pairs. And then when you look at this one, you can see that this one goes nicely with this one. Ammonium ion with ammonia and fluoride ion with hydrogen fluoride. So you can see that we have NH4 plus going with what? With NH3, and F minus going with what? With HF. So this is what an examiner expected you to do in terms of identifying conjugate acid base pairs. Now the next question is define an acid and base according to Arenas and Laurie-Bronsted and give examples. I think we have already defined an acid and base according to Arenas and Bronsted theories or principles, where we said an acid is a substance that can produce hydrogen ion. A base is a substance that can produce hydroxide ion. That was according to Arenas principle. And then Laurie-Bronsted said an acid is a proton donor and a base is a proton acceptor. And in terms of the Laurie-Bronsted theory, you can show that an acid like this, you can give this example whereby hydrochloric acid donating a proton and giving ammonium and chloride ion. Also, in terms of Arenas, you can just show that HCl can dissociate in water and give H plus and Cl minus, or potassium hydroxide can dissociate into K plus ion plus OH minus, because according to Arenas, you want to see whether H plus or OH minus is being produced. So those are the examples that the examiner is expecting out of you. But you need to make sure that immediately when they say give an example, you give an example that will be according to that theory. If it is according to the proton donation, you need to show protons being donated. If it is according to being hydrogen ions being produced, you need to also show hydrogen ions being produced in that example. So these are the possible solutions for the activity that you just done now, whereby HCl is with Cl minus, NH3 is with NH4 plus, NH4 plus with NH3, F minus with HF. And we can see always that a base will have one hydrogen short as compared to its conjugate acid or with its acid. Now, this is what I was explaining in terms of what an examiner will expect to see in terms of proton donor, proton acceptor, and in terms of producing of H plus and OH minus. So it is very important that you know how to explain those principles also in terms of the equations. Now, when we are talking about neutralization, the word says itself, it defines itself, neutralize. So when we neutralize an acid and a base, it means the substance that will be formed, it will not be an acid and it will not be a base. It will be neutral. So in terms of the neutralization reaction, we are going to look at the reaction between acids and bases. There is a difference between dilution and neutralization. When you dilute, you are making an acid and a base to react with water. That is not neutralization. That is pure dilution. But when you make an acid to react with a base, you are now doing neutralization. Just like the question that was asked now to say, how can I hydrolyze lime water, which is calcium hydroxide? So when you look at this one, I'm going to look at acid-base reactions. So when hydrochloric acid reacts with sodium hydroxide, I know that I'm going to get sodium chloride and water. So sodium chloride will be my neutral salt. So this solution at the end will be neutral. However, the strength of an acid and a base can also affect how the neutrality of a salt that will be formed, because we expect an acid, when it reacts with a base, to form a salt, and we always expect that salt to be neutral. So sometimes you'll find that the strength of an acid and a base that are reacting is not the same. So therefore, you need to check first whether there's the acid and the base that are reacting are weak or strong, or they are both strong, or the other one is weak and the other one is strong. I think it will also try to explain what was meant, or what was the question in terms of how do you do hydrolysis, or how do you hydrolyze. Now, when you look at our first example, already we have identified a hydrochloric acid as a strong acid, and we have identified sodium hydroxide as a strong base. So this one is a strong base, this one is a strong acid. So if you have a strong acid and a strong base, they have the same strength. It means their strength are gonna cancel each other because they are both strong. They can both dissociate completely. The other one can ionize completely. Therefore, what type of a salt are you going to expect? You will expect a neutral salt because you are reacting a strong acid and a strong base. So, in terms of the strength of the acid and the strength of the base that are reacting in terms of neutralization reaction, you will also know the type of a salt that will be formed in that reaction. When you look at the second example, sulfuric acid and sodium hydroxide, they are also strong acid and strong base. Sulfuric acid is a strong acid, sodium hydroxide is a strong base. So when they react, they will form sodium sulfate salt. So sodium sulfate, you can proudly say is also a neutral salt because it's coming from a strong base and a strong acid. Now there are instances now, like the last example, where we have ethanoic acid and potassium hydroxide. Potassium hydroxide is also another example of a strong base, but ethanoic acid is a weak acid. So we have weak acid and is reacting with a strong base. This is going to be furtherly explained in our next slide. So in this instant, we are going to get potassium ethanoate and water. So in this case now, you cannot say or safely say potassium ethanoate is your neutral salt. It is because now the strength of the acid and the base, they are no longer the same. This one, remember, it ionizes partially, whereas this one, it dissociates completely. So it means now the strength will differ. So the one that is stronger will definitely overcome the one that is weaker. So instead of this potassium ethanoate being a neutral salt, it will become a basic salt. It will not be neutral. This is nicely explained by hydrolysis, because as we are going to look at hydrolysis, we are going to say, why are you saying this is a basic salt? What is it that makes you to see that this is a basic salt, or what makes you to see that this is an acidic salt? So what is going to happen? We are going to use hydrolysis to explain this, because we are going to take that specific salt that will be formed and we are going to make it to react with water, because according to hydrolysis is the reaction of salt and water. As the salt will react with water, I will just write here hydrolysis, because I'm going to eat now. Hydrolysis is the reaction of salt and water. Where are these salts coming from? The salts are coming from neutralization reaction, whereby acids reacted with bases. So after an acid react with base, we are going to make that salt to react with water, so that we can see whether that salt is acidic or basic. If the salt is neutral, it means the acid and the base that were reacting were both strong. However, if the salt is acidic, it means the acid was a strong acid and the base was a weak base. But if the salt is basic, it means the acid was a weak acid and the base was a strong base. So let's go to, so as we are going to look at the reaction, before we look at the pH, we are going to look at the salt that is from an acid which is strong and the base which is strong. We said the salt is going to be neutral. So a neutral salt like hydrochloric acid reacting with sodium hydroxide, we are going to get this one, and we already know that this is going to be a neutral salt, because we know these two acid and the base are strong acid and a strong base. Then when we have a strong acid and a weak base, we are going to get an acidic salt, which is ammonium chloride. Now, how are we going to see that ammonium chloride is an acidic salt? We will make this ammonium chloride to react with water. So when ammonium chloride, you see there's ammonium ions. Let me just Okay. In ammonium chloride, there is ammonia. Let me just get the eraser here. I just want to erase this. Okay, it does not. Okay, it does. I just want to. Okay. What I want you to know is that. Okay. Oh, what have I done? Oh, I think I've just switched off everything. Okay. Sorry about that. This ammonia. Okay, let me just get my pen again. This ammonia will react with water because there are two ions involved here. We have the ammonium ion. I'm just trying to get my pen back. Okay. Okay, I think I'm fine. If we are having ammonium chloride, if we are having ammonium chloride, it means we are having ammonium ion and a chloride ion in it. Okay, let me choose ink, this one. Okay, fine. We are having ammonium ion plus chloride ion. So if you are having ammonium ion plus chloride ion, it means the chloride ion cannot be able to donate anything. But if you look at ammonium ion, I think we already know that ammonium ion is formed from this one is too thick. Yeah, let me choose this one. This ammonium ion is formed from this technology thing can sometimes mess you up. I think I'm fine now. Ammonium ion, we know that it is formed from ammonia after getting a proton from an acid. So this ammonium ion can easily be able to donate a proton. And as this ammonium ion can easily donate a proton, it becomes ammonia. So what happened is that in this NH4, this ammonium chloride, you will find that ammonium ion, which is having chloride ion, will react with water. And what is going to happen is that ammonium ion will give water a proton and we have H3O plus. And then what is going to form is going to, after losing a proton, it's going to form what? NH3. Meaning that now this H3O plus, when it is formed during the hydrolysis, it is a clear indication that ammonium chloride is an acidic salt. Why acidic salt? We know that for an acid to be present, ammonium, hydrogen ions or hydronium ions must be formed. So because ammonium chloride is forming H2O plus ions, it's a clear indication that this ammonium chloride is an acidic salt. When you look at chloride, it can still go this side and become chloride. So it's our spectator ion. The chloride ion doesn't participate in this reaction. It started being chloride ion on the side of the reactant. It will still be chloride ion on the side of the product to show that it never participated in this reaction. But who participated is the ammonium chloride, is the ammonium ion and water, because ammonium ion acted as an acid here and water acted as a base. So what happened is that as ammonium ion loses a proton to water, water gain that proton and become a hydronium ion. So the formation of hydronium ion is a clear indication to say ammonium chloride is an acidic salt. So immediately after getting the salt from the reaction of an acid and a base, make that salt to react with water. If that salt reacts with water and you find the hydronium ions, that is an indication that that salt is acidic. If the salt gives you a hydroxide ion, it will be an indication that that salt is a basic salt, like the example that is going to follow. Sodium hydroxide reacting with ethanoic acid to form what? Sodium ethanoate and water. So what I'm going to do, I will make this sodium ethanoate as my salt to react with water so that I check whether it's an acidic salt or a basic salt. So sodium ethanoate is CH3, COONA, and then plus H2O. Now, what is important is that what are the ions that are making this salt is CH3, COO minus plus Na plus, and then reacts with what? With water. Now, when you look at CH3, this Na plus will not gain anything. But what is going to happen is that is our spectator ion. What is going to happen is that this ethanoate ion, you can see that it's already missing something. It needs something because it's already minus. So water here will donate a proton to this one, to the ethanoate ion, and it will form CH3COOH plus. After water losing a proton, it will form OH minus. So OH minus is a clear indication that sodium ethanoate is the basic salt. So what am I saying? I am just saying to you, for every neutralization reaction, make sure that the salt that is going to be formed, you make it to react with water. Why are you making it to react with water? You want to check whether that salt is acidic or basic using the process which is called hydrolysis, because you are going to make a salt to react with water so that you can see whether you are forming H2O plus ions or you are forming OH minus ions. If you are forming H2O plus ions, it shows that that salt is acidic salt. If you are forming OH minus ions, it shows that that substance is a so the OH minus indicates that this is the base. The H2O plus indicates that the salt is acidic. So if you are having calcium hydroxide is a strong base. And if calcium hydroxide is a strong base, because the formula is Ca and then OH and then 2. Calcium hydroxide is a strong base. So for you to neutralize it, you will definitely need a strong acid. That is why when I started, I said you must be able to identify the acid as being strong or weak, bases as being strong or weak. So this is one of the example of the strong bases, because their constant equilibrium constant is greater than 1. The examiner most of the time will give you the equilibrium constant so that you know, or you can be able to identify it as a strong acid or a strong base. So this is just a chart to say, how can we identify them as strong acid, weak acid, strong bases, and weak bases? And we know that also when acids and bases are reacting, sometimes it is not easy for you to see whether they are now neutral, they have now reached a neutral position, or sometimes we refer to it as an endpoint where an acid neutralizes a base or a base neutralizes an acid, where we are going to look at it when we do titration, which is a neutralization reaction using a specific method. So we always use an indicator to see whether that acid on that base has neutralized each other. And there are 3 indicators according to the exam guideline that you must know, because we'll be dealing with some confined acids and bases in our topic. So I'm going to tell you the indicator that is suitable for each and every reaction. However, it is not going to be easy for you to be able to identify the suitable indicator if you cannot identify an acid being weak or strong, or a base being weak or strong. So the first thing that you need to understand is that you need to know that if an acid is a strong acid and a base is a strong base, the salt will definitely be neutral, because the pH will be equals to 7, approximately 7. Sometimes we need not to use the word equals to, is approximately 7. Therefore, if the pH is approximately 7, it shows that that specific solution that is formed, it is neutral. Then what is a suitable indicator that will show you that neutralization reaction has taken place? We are using what we call bromothymol blue. So bromothymol blue, you will choose it as a suitable indicator if you know that you are working with a strong acid and a strong base. When is this neutralization working in our daily lives? We know that we have sometimes having this thing that is called heartburn. So we normally know that heartburn is an indication of more acid in our stomach. Then how do we normally neutralize it? We know that there are some tablets that we can use to neutralize that acid, so that if the acid is being neutralized by that base that you will be ingesting, you will know that at the end of the day you will feel better. So neutralization reaction can work in our daily lives. You know how to neutralize an acid. If accidentally you pour yourself with an acid, if you don't want that acid to harm you, you will know that I must neutralize it, or I must wash myself with a base, because that acid will not have that acid property anymore, because that base will neutralize it. So you cannot pour sulfuric acid and expect to neutralize it with water. What will water do to it? It will just dilute it. It will still be a sulfuric acid. It will still maintain its property of being an acid. So you'll still get harm if it happens that you are neutralizing an acid with water, because it won't be neutralized. It will only be diluted. So neutralization will cancel the effect of being an acid or a base. And we know that we neutralize an acid with a base and a base with an acid. It is very important to understand that. So the indicators are the ones that are going to show us that the neutralization has already taken place. So bromothymol blue is an indicator that you will use only if you know that you are working with a strong acid and a strong base. If you are working with a weak acid and a strong base, the solution, of course, or the salt will be basic. So if the salt is basic, what is the name of the indicator that you can use to show you that neutralization has taken place? It's called phenolphthalein indicator. Phenolphthalein indicator, it is having a pH which is greater than 7. We know that according to the pH scale, the pH scale ranges from 0 up to 14. So less than 7 is all acids. More than 7 are all bases. So in terms of less than 7, we also know that we have strong acids and strong bases. So if the numbers like 1, 2, 3 is the pH of an acid, we know that it's a strong acid. 4, 5, 6, close to 7 is a weak acid. And then closer to 7, going to maybe 8 or 9 is a weak base, and then 10, 11, 12, 13, 14 is a strong base. So the pH will also indicate to you whether the acid or the base is a strong acid, weak acid, is a strong base, weak base. Now, you need to know now if you have a strong acid and a weak base. If you have a strong acid and a weak base, we're going to get an acidic salt. Now, which indicator is important or is suitable to show the neutralization of that reaction? We name it methyl orange. Methyl orange is an indicator that we are going to use as long as we are sure that we are working with a strong acid and a weak base. Methyl orange will be the one that we'll be using to indicate the neutralization. Why? Because the pH of methyl orange is less than 7. And we know that the pH of all the acids are less than 7. Of all the bases are greater than 7. Neutral, they are approximately 7. So these indicators, the examiner can sometimes ask, which suitable indicator can we use for this reaction? What is it that you must identify first? You must identify whether that acid is a strong acid or weak acid, and therefore you can choose. Like this example, if you look at this reaction between hydrochloric acid and ammonia, first of all, you know that hydrochloric acid is a strong acid. So this is a reaction of strong acid and weak base. So if you have to find this ammonium chloride in your reaction as the neutralization reaction, you know that for the strong acid and the weak base, what type of an indicator must I use? You know here that in this reaction, you must use methyl orange because you are working with a strong acid and a weak base, according to the table that I provided here, to say you need to identify them first. So if you don't know the name of the acid and if you don't classify them as strong or weak, definitely you are not going to be able to choose the suitable indicator. You must start back there by being able to identify them as strong and weak first before you can choose the suitable indicator, because the indicator, they are chosen because of the scale or the pH scale. We are going to calculate pH, but let me not do the calculation of pH right now. I want us to just look at because our time is almost up. I want us to look at the exam type of questions and see how the examiner can ask questions on under acids and bases. So what we are going to do in our next on our next lesson, we are going to look at the pH calculations, and we are also going to further look at the other calculations that are pertaining these neutralization reactions. But for now, I want us to look at this activity and see whether we can be able to answer some of the questions that can be examinable. Now, they are saying here, anhydrous oxalic acid is an example of an acid that can donate 2 protons. And you say an acid that can donate 2 protons is underlined, and thus ionizes in 2 steps. As I said that because as it is having 2 protons, it means it can sometimes ionize in 2 steps. Now, as represented by the equation below. So the anhydrous oxalic acid is ionizing. Here it is reacting with water to form hydronium ion and this oxalate ion. And then oxalate ion reacts also to form hydronium ion and this. So what is happening here is that you need to firstly identify your reactions and understand and read your reactions. The first thing that I think you need to know, you need to understand which one is the reaction, is the acid in the first reaction, and which one is the base in the first reaction. Also, which one is the acid in the second reaction and which one is the base in the second reaction. So it is easy. As I said, for the first reaction, you are just going to ask yourself, okay, let me look at the relationships. This one is having CHOOH2 and then H2. So H2O is formed. H2O plus is formed. It means water has accepted a proton to form this. And then this one, as it was losing a proton, it formed this. So this one is my acid here, and water is my base here. This one will be my acid on the side of the reactants, and this one is going to be my base. Then, and this minus and the H already tells you something. It tells you that this substance can sometimes donate this hydrogen or can sometimes accept. So already what comes into your mind is the issue of an ampholyte, to say this substance can be an ampholyte because it can act as an acid and it can also act as the base. Minus makes it to act as the base. H makes it to act as an acid. And then this one also donated now a hydrogen to water. And we can see it forms this and this. So we have already identified your acid-base pairs. So what are the questions? One word of the underlying phrase, an acid that can donate 2 protons. We know that we said is a diprotic acid. So a diprotic acid is an acid that can donate 2 protons. And then the formula of each of the 2 bases in reaction 2. In reaction 2, as we said, this one will act as an acid, this one will be our base, and this one will be our acid, and this one will be our base. So our bases in reaction 2 is HCOO, and then minus 2, and COO, 2, and then 2 minus. This is our bases in reaction 2, because they are both bases, the water, and what is it? No, the basis is the not this one. This one is an acid, H2O, and this one, remember, it donated a proton to water. So our base is water as I identified it, and this one. So it's H2O and this one, which is our basis in reaction 2. But you can see that our ampholyte is this one, and this one is our ampholyte. HCOO 2 minus is our ampholyte. The formula of a substance that acts as an ampholyte in reaction 1 and 2, I think I've already identified it as this one. Give a reason why oxalic acid is a weak acid. Oxalic acid is the weak acid. I think we have explained it. Oxalic acid is the weak acid because it ionizes incompletely in water. So it is very important that you remember all the definitions. You just say why it is referred to as a weak acid. It is because it ionizes incompletely. So it is very important to remember all the definitions. We started with looking at the 2 principles, Arena's principle, Lori-Prostit principle. We classified acid as weak and strong, bases as weak and strong. We also look at acid-base conjugate pairs. We also look at acid-base reactions, which is neutralization. I also explained hydrolysis reaction, whereby after getting a salt, you will make that salt to react with an acid so that you can see whether the salt that is formed is acidic or basic. So as we are going to continue in our next on our next lesson, we are going to see how now are we calculating the pH that we are saying the strong acids are having this specific pH, weak acids this specific pH, strong bases and weak bases. So we are going to continue and look at how do we calculate the pH of different acids and bases. Now we have just come to the end of today's lesson. Thank you so much for watching this lesson. Please remember to sanitize. Always make sure that you wear your mask and you maintain your social distancing. Till the next lesson that is going to come next week is goodbye for me. Thank you so much.